Okay. I have to finish the proof, postponed from the late lecture. I have to recall the formulation. And proof from lecture 5. Our subject was the analog of Poincaré-Virchow-Witt theorem for the Yangian I reduced this claim to the following one. Instead of a Yangian, we are dealing with the associated gradient algebra, which is the algebra of polynomials. And the claim is polynomials, symmetric algebra. Of, it's not correct, I'm sorry. It's not correct. The claim is as follows. I'm very sorry. The idea is as follows. We claim to prove is as follows. So we fix a natural number m bar, and the claim is that there exists n prime, another number, such that we consider the elements J prime, where the restrictions on the indices are as follows. We fix m and these are elements of a symmetric algebra. As follows: a sum of and we assume that the range of this index m is bounded by some bound m bar. And the claim is that these elements are algebraically independent, provided that n prime is large enough. So I proceed to the proof. So the proof. First step is to realize realize the symmetric algebra prime is the algebra of polynomials of the matrix argument X, which is a matrix of the size n prime. One write as follows. And then our elements turn into polynomials. Which are as follows. The polynomials of X, this matrix argument, which are defined as follows. We take X, this is a large matrix. We raise it to the power m and take the entry I and j. I recall that these entries are subject to this restriction. And we claim that these polynomials are algebraically independent or large and prime. How to do this? The idea is to restrict. We will restrict them to an affine subspace. Of this matrix space in such a way that under this restriction they behave nicely. So it will be almost evident why they should be algebraically independent. So consider triple indices. See the triple indices I, j, and m, which form a finite set because we have this restriction. N is fixed, and m is also bounded. So we have some finite set of these three indices. And to any triple of such kind, we assign a subset. I will denote it as follows. Subset which is contained in this finite set in such a way that the size of this subset is equal to m minus 1, and all these subsets are disjoint. And this is possible if n prime is large enough, which is possible, for n prime large enough. And then I regard our matrix space as a set of operators. So this matrix space, the space of operators. And I define an operator as follows. For any triple, I assign an operator, a particular operator, which looks as follows. So let me draw a picture. So given this triple, I want to enumerate the points of my subset in some way. For instance, for definite, it's not very important. This subset. And the corresponding operator looks as follows. Let us choose the canonical basis of our space. Canonical basis. Canonical basis. Something like this. And next, very, very, very large sequence as follows. And I assume that the operators give the follows. Let me draw a picture. These are some basis elements. Here is I, J. This is and the operators does the following. This vector, it moves to this one, and this is moves here, such a chain. We arrive at this point, and next it is moved to this vector with multiplication, by a parameter. I need one parameter attached to any such subset, some numeric parameter. Some numeric parameter, say this one, which depends on our subset. And finally, I want to take X. So we get some subspace, some subspace, which is spanned by such vectors, which are here, and the vectors which belong to the union of all basis vectors, which are parameterized by indices from our subsets. So take this sum. So what is this? This is an undefined subspace. Undefined subspace. Subspace of with coordinates finitely many coordinates. And now let's analyze what happens if we take our matrix, and fix I, J, and M, and what happens? What happens? The idea is, looking at the picture, we see that the corresponding polynomials looks as follows. It contains this letter, and the rest term is some polynomial in some other parameters, variables. But what is important? That L is strictly less than M. From this is easy to see from the construction. And from this picture, it becomes more or less evident, I hope, that such polynomials are algebraically independent, because we have a kind of triangular dependence on the coordinates. These leading coordinates, we have some leading coordinates, this one, which corresponds to this triple, plus the rest, which depends on coordinates with a smaller index L. And from this picture, it's clear that we have algebraic independence. So let me stop at this moment and ask if there are some questions about this construction. Please ask. Okay, so at this moment, I finish with the subject of Poincaré-Birgov fit, and let's start another topic, which I call quantum determinant. So this is a long story. I think I cannot finish it just today, and I will continue in a week. So what is the subject? The idea is what the problem is under which assumptions one can define a determinant of a matrix with non-commutative entries. So assume we have some algebra, possibly non-commutative algebra. And we have a matrix X, which is matrix some size with elements in this algebra. So what is determinant? In such a general setting, it's impossible to define a good notion of determinant, because we want that for instance, we want something like multiplicativity property. the determinant of a product should be the product of determinants, but for non-commutative, in the case of non-commutative entries, this does not hold in general. And moreover, it's even impossible in general to define what is determinant. For instance, if you have a matrix, so look, we have a matrix, say 2 by 2, then the usual formula says that we have minus. But if the entries do not commute, we don't know what is this one, or for instance, this one. So the problem is to give a meaning to this expression. There are some possibilities. So one can define the one version is a column determinant of X is defined using the column expansion. So we, by definition, we take the sum of permutations in n letters, the sign of the permutations plus minus one as usual. Here we write but of course there is a possible variant, another variant of this definition, which is quite similar but different. One can write as follows. In the commutative case, this is the same, but in the non-commutative case, these two variants are quite different. And now I want to address the problem related to the center. Recall that I spent some time to discuss some questions related to the center of a universal enveloping algebra, GLN. And I constructed a sequence of elements, sequence of central elements. I recall the definition. This is the formal trace of the mth power of our matrix, which I used many times. I call its definition. A matrix formed by matrix units. And it is not difficult to prove, I did that these are central elements and they generate the center, provided that the index m takes the value 1 until. And now I want to discuss another construction. So we discuss another construction. Namely, this construction also depends, as in the case of Perelomov-Popov theorem, it also includes some parameter, some formal parameter, which is useful. So the construction involves some generating series, but in fact, a generating polynomials, not a formal series now, but a generating polynomials. The definition is for U is my formal parameter, and I defined it. This is some element of the universal enveloping algebra depending polynomially on our parameter, and it is defined as the column type determinant of some matrix, which looks as follows. On the diagonal, we put this matrix unit, and next. And the end we have and the off-diagonal elements are the same as are in our matrix, this one. So here we have and so on. And likewise, we have such a matrix. And the determinant is defined via expansion in columns. It can be also written. So this is our matrix, and plus a diagonal matrix.
Can I ask a question?
Yes, of course.
What's the usual... какие свойства определителя сохраняются на вот это CDET и RDET?
Погодите, Ира. Все будет в общем виде, ничего не могу сказать. Но в некоторые конкретные ситуации будет сформулирована теорема. А в общем,
хорошо, спасибо.
Такое особенно ничего не могу. Ну, можно там, я думаю, такого рода определитель выдерживает элементарные преобразования, наверное. Я так думаю, да. Там нужно только сообразить по строчкам или по столбцам. На таком уровне, но не более того, наверное. Сейчас я зажгу свет. So this is the definition. So I'm sorry, excuse me, just a moment. So what is this C of U? It can be written something like this. So we have
То есть это как бы на Гамильтона-Келли похоже, да? Раньше мы писали свет, а теперь мы такой как бы характеристический
как бы похоже на характеристический многочлен. Да. Гамильтон-Келли, кстати, мы до него дойдем, он имеет место. Гамильтон-Келли. So we have such a polynomial, and now the claim is as follows. First claim is that this element is in the center. This is the first claim. The second claim is it provides generators, algebraically independent generators of a center. So the whole center is isomorphic to the algebra of polynomials. Let me explain now. The proof is rather long. So I want only to point out the idea of the implication. Idea of implication. So assume that the first claim is already proved. Why? The second claim will follow. The idea is similar to the idea behind the Perelomov-Popov theory. So what we want to prove? We want to establish to use the map. To use the map from the center to shifted symmetric polynomials. Shifted symmetric polynomials in highest weight coordinates So I assume that lambda is a signature. I recall that this is signature is an n-tuple of integers, and signatures parameterize finite dimensional representations. So to any signatures, there corresponds an irreducible finite dimensional representations. Irreducible finite dimensional representations of our algebra. And by Schur lemma, any central element is given by a scalar matrix. And the corresponding scalar can be computed, for instance, by applying our central element to the highest weight vector. So this is highest weight vector. It is convenient to use it because it is annihilated, it is killed. It's 0 for any upper diagonal generators. So we know by some general formalism that there is in fact an isomorphism, isomorphism with the algebra of symmetric polynomials in shifted coordinates. Shifted coordinates, where I recall the definition. This is a shift. So now, assuming that our element is central, we want to apply it. Look what happens when we apply it to this vector. I claim that the result will be as follows. The result will be as follows. And because this, I will explain why this happens, these diagonal generators act on the highest weight vectors by the corresponding coordinates lambdas. So this is the same as this product. And this quantity, this scalar, is simply equal to the product or maybe it's convenient to rewrite this where V is equal to U And from this expression, we see that it's indeed the generating function, generating polynomials for the elementary symmetric polynomials in this coordinate. So it remains to check why. I'm sorry. It remains to check why the action of these elements reduces to this. But it's easy to see. So look at, we expand this determinant. So what we have to do, we have to pick some entries here and apply it. But because this is erasing operators, it annihilates our highest weight vectors unless we have these entries. And we repeat this picture, and the result is as follows. When we apply the expansion of this determinant, the only non-zero contribution comes from a single product, which is related to the diagonal. So this is very easy. So let's compare this construction with the Perelomov-Popov theorem. There is different, they are different in the following aspect. In the Perelomov-Popov theorem, it's rather easy to prove that the elements are central. In the Perelomov-Popov case, what is this? I'm sorry. Okay, so the construction provides central elements in the Perelomov-Popov case. This is easy. What is not trivial is the computation of the corresponding eigenvalues. But here the situation is just the opposite. You see that computing the eigenvalue is almost trivial. But to prove, yes, what this case is the Perelomov-Popov. But in this case, it's much more difficult to prove that this is indeed a central element. So this is non-trivial part of the proof. But I want, this can be proved independently of the Yangian theory, but I want to prove a much more general, powerful result, which is related to this, which is something similar, but in the case of a Yangian. So we return to the Yangian. I recall that the Yangian is generated by the letters, this one, formal letters. And in terms of a generating series, let me recall generator series. In terms of generating series, I'm sorry. I need to recall the matrix Q of U, which is composed from this generating series. This matrix can be viewed, if you want, as a matrix of size n with the entries in the Yangian, but okay, one can add. And now I defined the quantum determinant. Of this matrix. The definition is as follows. It can be denoted as follows. This is my notation, but I will use the shorthand notation D of U. So D of U will be something like this. With I some elements by Yangians, and the definition is as follows. D of U is by definition, we take the sum over the symmetric group and so this is the definition.
Ты большой с двумя индексами, то же самое, что ты маленькая с двумя индексами, да?
Да. Спасибо, вы правы. Вы правы, давайте я исправлюсь. Это я напрасно. Это я погорячился. Спасибо большое. Да. Да. Вот так. Вот это определение. This is the definition. So we claim, you can guess already. So this is a central element of a Yangian. So the proof is long, and it is based proof long based on the fundamental RCT relation. But let me first of all explain why this result implies the previous theorem. So let me put it theorem 2, and in the end, this will be theorem 1. So I want to show we claim. So theorem 2 implies theorem 1. This is easy to see. We use the truncation homomorphism. Truncation homomorphism. And I recall what is its definition. So psi of this, and over high elements are killed. Now we recall the definition. We recall the definition that T. Maybe let me just skip because it's easy. It's easy, almost trivial. Okay, maybe I will write. So what happens with this matrix after entry-wise application of this psi? But this is nothing as our matrix E multiplied by this. Maybe it's better to. I'm sorry. Maybe I'm wrong. No, it's correct. It's correct. It's correct. Only it's useful to rewrite it as follows. This way. And using this, and because of the shifts, of these shifts, we just obtain the element C of U up to a scalar product, the product of U multiplied by U minus 1 and so on, which does not affect the result. Some questions maybe at this moment. So I repeat, so we have this homomorphism, so the center is mapped to the center. So this is a quick corollary. Now I want to proceed to the proof for the Yangian, which consists of several steps. So I recalled first the basic identity, the RTT identity. Let me write it in a slightly different notation. Not U and V, by U1 and U2. The whole theory relies on this basic, fundamental relation. I recall the definition of the Yang R matrix. And this is an operator in this auxiliary space, which we use. And I recall that we have the tensor product, the Yangian, and these elements operate here and here. It is an element of this tensor product, and here we have the identity operators, and T2 do the same with respect to this couple and acts trivially here. But now I want to prove some generalization of this fundamental relation. The generalization looks as follows. Let me introduce the notation V is our auxiliary space. And I also need not to by some arbitrary number of copies. So these are copies of this space. And instead of U and V and U1, U2, I need M formal parameters. But commuting parameters. Maybe they should be called spectral parameters, but this is just a word, nothing more. And instead of this ring of formal power series, I will deal with many formal variables. But actually, I will also use some mild extension of this space. What next? So instead of two-fold tensor product, I will need M-fold tensor product, which I write as follows. All the spaces are the same, coordinate space Cn. Next, instead of R of U or this one, I will need something more general. I want to use some shorthand notation. I will explain in a moment. So I need to add to my space the inverse or inverses of these elements, but this does not cause any problem. But what is this? So this is the R matrix. The R matrix acting on I and J copies only. So we have some big product, this one, and we pick some two copies, number I and number J, which are different, and we consider the R matrix, which acts as an R matrix and acts trivially on all remaining subspaces. Next, I need the T matrices. This is again a shorthand notation. So let me write in more detail. What is this? Matrix units in the copy number I. Some questions on this notation? Is it clear? Okay. And this is in this position. What? I need one important notation. This is by definition the following multiple product. Let me write it from right to left. First, I write this one. Till I have in mind what I have in mind. Have in mind this notation. Okay. So I use it and I write. This is the first product. Next, I begin here. The index is 1. Now I begin with 2 instead of 1. So and so on. In the end, I have only one. Such a thing. So for example, to say m is equal to 4. So is the following. So I hope is it clear? This is clear. If not, please ask me about this definition. Okay. And now the proposition I want to prove. Have a generalization of a fundamental relation, which looks as follows. For any m, we have on the left and on the right the same operators, but written in the reverse order. So the claim is that this complicated R matrix, some analog of R matrix, is used to reverse the order of this in this product. Just as in the basic case when m is equal to 2. So this is evident generalization. So the proof in 2 steps. Some tricks, not very difficult, but some technology. I would like to explain this technology of R matrix formalism. So the step 1. Step 1. Write the left-hand side. So no, I'm sorry. Take one product of this generalized R matrix. Take only this product. So this corresponds to the first product on the right, this one. And write our operators, T1, but the rest. And to better understand the idea, maybe I will denote this as with tilde. These indices 1, 2 are related to this one. And this product, let me denote as T2 tilde. And here, 2, the index 2 is associated to the first term of this product. And the claim is that we have an analog of the RTT relation. Which is written as follows. You can guess probably already. So using this matrix, I say matrix, but this is some operator in the tensor space. It allows us to change, to reverse the order. So this is the claim. This is the claim. Claim of step 1. How to prove? Not difficult, but some ideas are used. The left-hand side, write it in more detail again. So we see, it's evident that we have this quantity and we want to interchange T1 and T2 using this nice R matrix. So let's do this. So we write this. And now with quantities is replaced by this one. And the rest is the same as before. But what happens now? The idea is simple but very ingenious. The idea is as follows. So this term commutes, this matrix commutes with all these guys. From the very definition, the idea is these indices are distinct from all these indices. And using this observation and the very definition of the R matrix, because it produces something in the first 2 copies of our tensor space, of our multiple tensor space, these quantities are related to the remaining copies. So we can put it on the right. This. And likewise, this term also commutes, and it can be moved here. And after this transformation, what we get something like this. And now we repeat this story. Repeat this story. Repeat this story again and again. And after this, in the end, we get the desired result. All this chain, maybe I don't want to, sorry. All this is finally permuted with this element in the end. Now step 2 is actually the iteration of the same procedure. So what we have in step 2, so we observe that we have with and I played with this. But now we can repeat the story. So repeat the same with T2 instead of T1. So we can forget about T1 and do the same with T2 and etc. So looking a bit more closely on this picture, you arrive at the result. So this is the end of this proposition. The next topic, next part of the proof of our theorem is related to some very nice, I think, very nice story about simply the symmetric group. The story is about the antisymmetrizer in the symmetric group. What is the antisymmetrizer? This is an element of the group algebra. Its definition, I think, is clear. The alternating sum of all permutations. Sum over all permutations. This is a central element. Central element, it's easy to see. of our group algebra, and up to a scalar product, it is an idempotent. But let me postpone this discussion. So, for instance, we have this identity. This is my notation for the transposition. More generally, these are odd permutations, and we have two. Let me write it. Two cyclic permutations which are even, and so on for any m. But now we have a truly, I think, a truly remarkable result. Another proposition. The claim is factorization. Factorization of the antisymmetrizer. The claim is as follows. I will write and then explain what I mean by this. The picture is similar to the definition of this complicated analog of R matrix. So I only need to explain what is Sij in my notation. It's something which is strongly resembles to the R matrix, but only regards it as an element of a group algebra. So look, this is something miraculous, I think. This factorization. And it is not trivial at all. Not trivial at all. I hope I have time to give a proof of this result. So the proof. So it's easy to see that the left-hand side, so simply AM, can be written as follows. I will write and then I explain. These are transpositions. And what is this? The antisymmetrizer corresponding to indices 2m. So this is actually the antisymmetrizer in the symmetric group, which fixes the point 1 and permutes 2, 3, and so on till m. Is it clear with my notation? Okay. So this is easy to see. This is trivial. This is rather trivial. But by induction, using induction, induction on M, our claim reduces to the relation maybe I will write it as follows. So this is actually AM, and I want to prove that this is the same as so let me emphasize that this is the result concerns only the symmetric group, nothing else. I don't think that this is a well-known result. So how to prove this? How to prove this? We need a lemma which says the following: for any k tuple of indices strictly decreasing, so for any k tuple, the following relation holds. This anti-symmetrizer being multiplied by such a product is the same as the same so this actually we have this relation. So we just manipulate, just write what is this product, and we write it as follows. So this does not depend on this factor. This is some identity, simple identity, but then
So, sorry, may I ask, in sigma I1, IK, maybe, I don't know, either...
No, you are right, you're right. I'm sorry, it's incorrect. You're absolutely right, and thank you very much. This one, thank you. So the idea is that these elements, it lies in our subgroup, which is embedded. which does not involve point 1. And because of this is simply the same, and the property of the anti-symmetrizer. We have this a nice cancellation effect. So this is lemma. This is by the lemma. I just means this computation. But now we can write. So we want now to transform this expression. And how to do this? We write, let's denote it, say, by star. What is this? Write again. So we just open the parentheses, the brackets, I'm sorry, the brackets, and write this as follows. The sum over k. K is the number of terms we keep from this product. Now we have this factor which comes from the minus signs attached to these permutations. And next we have the sum, another sum over k tuples. Next we have this. But now we use the lemma. Now we use the computation in the lemma and the cancellation which comes, because we have exactly such a product which comes this together with this anti-symmetrizer. And we have this one which comes from this. Next we have the minus, which this minus comes from this sign and this one. And this gives us simply one minus. Next, we have the sum over the index r, which is actually the I sub 1 in the new notation. We keep this this comes from this term. And next we have to sum over k and over double sum over, because this is I sub 1, the former I sub 1. And what we collect these factors. We collect this factor, and this factor, it's here, because this index is R in my new notation. Maybe some questions about this transformation. Please ask if something is unclear. But the last step is to analyze this sum, this double sum. This double sum. Claim that it's equal to simply to and because of this claim, this is cancelled with this one, and we get, finally, we get exactly this expression. This is the end. So it remains to prove, so it's the end, it remains to prove the simple identity, a simple combinatorial identity, which looks as follows. So identity for any R, we have this is easy. This is very easy. This is something, the left-hand side can be written as follows. Something like this. Maybe I forgot. I think it's follows. -1 must be equal to this one. This is trivial. The reconciliation, because this is written as 2. So this is the end of the proof. Let me stop at this moment. So I would like just to repeat again that we have this remarkable factorization, but it's actually a simplest case of much more general relations in the symmetric group, which has some further generalization. So this is a long story and a very interesting combinatorial result. So let me stop at this moment. Let me switch off the stream.